Welcome. We are going to explore one of the most elegant ideas in all of science. The idea that every physical quantity can be expressed using just three fundamental building blocks: mass, length, and time. These are called dimensions, and together they form the backbone of the entire international system of units, which we call the SI system. By the end of this lecture, you will be able to look at any unit in electrical engineering, whether it is the volt, the ohm, the Farad, or the Tesla, and trace exactly where it comes from. You will also discover why so many of these units carry the names of brilliant scientists. Let us begin. Think about this for a moment. When you say the voltage is 230, what does that actually mean? Without a unit, the number is completely meaningless. Is it 230 volts? 230 millivolts? 230 kilovolts? This is exactly the problem that engineers and scientists faced for centuries. They needed a universal language, a system that every engineer in every country, in every era, could use without ambiguity. The solution was to identify a small set of base dimensions from which every other quantity in nature can be built. For mechanical quantities, the physics of objects in motion, just three dimensions are enough: mass, written as m, length, written as l, and time, written as t. For electrical engineering, we add one more: electric current, represented by the letter I. Everything else, force, energy, power, resistance, capacitance, inductance, is built from combinations of these four base dimensions. This is the genius of the SI system. Let us now look at each of the three fundamental dimensions individually. Mass, represented by m, measures how much matter is present in a body. Its SI unit is the kilogram. Mass is a scalar quantity, it has no direction. Importantly, mass resists acceleration. The more mass an object has, the harder it is to change its velocity. Length, represented by L, measures distance or extent of space. Its SI unit is the meter. Note that L appears squared when we deal with areas and cubed when we deal with volumes. And time, represented by T, measures the duration between events. Its SI unit is the second, now defined with extraordinary precision using atomic oscillations of the cesium atom. Exactly 9,192,631,770 cycles. Together, M, L, and T can describe every mechanical quantity in physics. Notice particularly how negative powers of T appear when we divide by time. That is how velocity and acceleration arise. Now that we know the three dimensions, let us learn how to read and write dimensional formulae. The general form is m raised to the power a times l raised to the power b times t raised to the power c. Each exponent tells us how that dimension is involved. Positive exponents mean the quantity increases with that dimension. Negative exponents mean the quantity decreases with it. Let us derive a few together step by step. Velocity is displacement divided by time. L divided by t, written as lt to the power minus 1. Acceleration is velocity divided by time again, so lt to the power minus 2. Force, from Newton's second law, is mass times acceleration, m times lt to the minus 2, giving mlt to the minus 2. Energy is force times displacement, adding one more l, so ml squared t to the minus 2. And power is energy divided by time, giving ml squared t to the minus 3. Notice the beautiful pattern. Every step simply multiplies by one more dimension. Once you understand this chain, you can derive any unit from first principles. Let us now derive our first named unit, the Newton, the unit of force. Newton's second law of motion tells us that force equals mass times acceleration, written as F equals m times a. Step 1. The dimension of mass is simply m. Step 2. From our previous slide, acceleration has dimensions lt to the power minus 2. Step 3. Multiply them together. Force has dimensions m times lt to the minus 2, which we write as mlt to the minus 2. 1 Newton is therefore defined as the force needed to accelerate exactly 1 kilogram by 1 meter per second every second. In full units, 1 Newton equals 1 kilogram times meter per second squared. This unit is named after Sir Isaac Newton, born in 1643 in Lincolnshire, England. Newton formulated the three laws of motion and the universal law of gravitation in 1687, work that remained the foundation of all mechanics for over 200 years. When you write N for force in any calculation, you are honoring the man who first mathematically described how the universe moves. Now let us derive energy. Work is defined as force multiplied by displacement. The equation is W equals F times D. We already know the dimension of force, mLT to the minus 2. Displacing an object over a distance adds one more factor of L. So get mLT to the minus 2 multiplied by L gives mL squared T to the minus 2. This is the dimensional formula for both work and energy. 1 joule is 1 Newton meter, which in base units is 1 kilogram meter squared per second squared. And if we divide energy by time, we get power with dimensions mL squared T to the minus 3. Power is measured in watts, named after James Watt, the Scottish engineer who perfected the steam engine and made the Industrial Revolution possible. James Prescott Joule, who gives his name to the unit of energy, made a monumental discovery in 1843. He proved that heat and mechanical work are exactly equivalent, laying the foundation for the law of conservation of energy. Now we reach the key extension for electrical engineers. The three mechanical dimensions M, L, and T are not sufficient to describe electrical phenomena. We must introduce a fourth base dimension. That fourth dimension is electric current, represented by the letter I. Its SI unit is the ampere. Now you might reasonably wonder, why is current treated as a base dimension? Could we not derive it from mass, length, and time? The answer is no. Electric charge is a fundamentally new property of matter. It has no mechanical equivalent. You cannot build electricity from gears and springs. It requires its own mathematical foundation. So the SI system recognizes current as an independent base dimension. This means that every electrical quantity will have at least one power of I in its dimensional formula. The ampere is named after André-Marie Ampère, a French physicist who lived from 1775 to 1836. Ampère was the first to prove mathematically that parallel wires carrying current attract or repel each other, the very phenomenon used to define the ampere. He is called the father of electrodynamics, and his name for the unit of current is well deserved. Our first purely electrical unit is the Coulomb, the unit of electric charge. We derive it from the definition of current. Current is the rate of flow of charge. In equation form, I equals Q divided by T. Rearranging charge Q equals current I multiplied by time T. In dimensional form, Q has dimensions I times T. 1 Coulomb is therefore the charge that passes when 1 ampere flows for exactly 1 second. Expressed in full SI base units, 1 Coulomb equals 1 ampere second. To put that in perspective, Coulomb represents approximately 6.24 times 10 to the power 18 electrons. That is 624 quintillion electrons passing a point in 1 second. The charge on a single electron is just 1.6 times 10 to the power minus 19 coulombs, an incredibly tiny quantity. The unit is named after Charles Augustin de Coulomb, a French physicist who in 1785 established Coulomb's law. The electrostatic force between two charges is proportional to their product and inversely proportional to the square of the distance between them. This law is the electrical equivalent of Newton's law of gravitation. Now we derive two of the most important quantities in circuit analysis: voltage and resistance. Voltage, also called electromotive force, is defined as the work done per unit charge. In equation form, V equals W divided by Q. Let us substitute dimensions. W has dimensions mL squared T to the minus 2 and Q has dimensions IT. Dividing mL squared T to the minus 2 divided by IT gives mL squared T to the minus 3I to the minus 1. 1 volt in base SI. Units is therefore 1 kilogram meter squared per second cubed per ampere. Notice the appearance of I to the minus 1. Voltage is inversely proportional to current for a given amount of energy. Alessandro Volta invented the voltaic pile in 1800, the world's first true battery, and demonstrated for the first time that electricity could be stored and released in a controlled, sustained manner. For resistance, we use Ohm's law, R equals V divided by I. Substituting dimensions, mL squared t to the minus 3I to the minus 1 divided by I gives ml squared t to the minus 3I to the minus 2. 1 ohm in base units is 1 kilogram meter squared per second cubed per ampere squared. Note, resistance gains I to the minus 2 because it involves two separate divisions by current. Georg Simon Ohm discovered this linear relationship between voltage and current in 1827. His law is so fundamental that it appears in virtually every circuit calculation you will ever make. Our next two units are capacitance and inductance, the two energy storage elements in circuit theory. Capacitance is defined as the charge stored per unit voltage, C equals Q divided by V. Substituting dimensions, Q has dimensions IDT and V has dimensions ml squared t to the minus 3I to the minus 1. Dividing IT by ml squared t to the minus 3I to the minus 1 gives us m to the power minus 1, L to the power minus 2, t to the power 4I squared. 1 farad in base SI units is 1 kilogram to the minus 1, meter squared to the minus 1, second to the power 4, ampere squared. Notice the negative powers of m and L. This makes physical sense. A larger electrode area increases capacitance, but we are dividing by the mechanical dimensions in the denominator. The farad is named after Michael Faraday, who began his career as a bookbinder's apprentice with no formal education. He became perhaps the greatest experimental scientist of the 19th century, discovering electromagnetic induction and the laws of electrolysis. For inductance, we use Faraday's law, V equals L times di by dt. Rearranging all L equals V times T divided by I. Dimensionally, ml squared t to the minus 3I to the minus 1 multiplied by t divided by I gives ml squared t to the minus 2I to the minus 2. 1 Henry in base units is 1 kilogram meter squared per second squared per ampere squared. Joseph Henry, an American scientist, independently discovered electromagnetic induction at approximately the same time as Faraday. Our final derived electrical units come from magnetism. Magnetic flux, represented by the Greek letter phi, is derived from Faraday's law of electromagnetic induction. The induced voltage equals the rate of change of magnetic flux V equals d phi by dt. Rearranging phi equals V times t. In dimensional form, ml squared t to the minus 3 I to the minus 1 multiplied by t gives ml squared t to the minus 2 I to the minus 1. 1 Weber in base SI units is 1 kilogram meter squared per second squared per ampere. The Weber is named after Wilhelm Eduard Weber, a German physicist who worked alongside Carl Friedrich Gauss to develop the first global magnetic field mapping system. Magnetic flux density B is simply flux per unit area. We divide by L squared, which removes two factors of L from the numerator. The result is mt to the minus 2I to the minus 1. 1 Tesla in base units is 1 kilogram per second squared per ampere. The Tesla is named after Nikola Tesla, who gave us the alternating current motor and polyphase power systems that distribute electricity across the entire world today. To put 1 Tesla in perspective, Earth's own magnetic field is approximately 25 to 65 microtesla. A hospital MRI machine operates at 1.5 to 3 Tesla, roughly 60,000 times stronger. Here is our complete master reference table. Every quantity we have studied in this lecture, listed with its dimensional formula in M, L, T, and I, it's named SI unit, and the scientist it honors. Let us read through together. Force, ml, t to the minus 2, the Newton, named after Isaac Newton. Energy and work, ml squared t to the minus 2, the Joule, named after James Prescott Joule. Power, ml squared t to the minus 3, the watt, named after James Watt. Charge, I times t, the Coulomb, named after Charles Augustin de Coulomb. Voltage, ml squared t to the minus 3I to the minus 1. The volt, named after Alessandro Volta. Resistance, ml squared t to the minus 3I to the minus 2. The ohm, named after Georg Simon Ohm. Capacitance, m to the minus 1 L to the minus 2t to the 4I squared. The Farad, named after Michael Faraday. Inductance, ml squared t to the minus 2I to the minus 2. The Henry, named after Joseph Henry. Magnetic flux, ml squared t to the minus 2I to the minus 1. The Weber, named after Wilhelm Weber. Magnetic flux density, mt to the minus 2I to the minus 1. The Tesla, named after Nikola Tesla. Memorize the derivations, not just the results. If you understand how each unit is derived, you can always reconstruct it. Dimensional analysis is not merely a bookkeeping exercise. It is a powerful tool that every engineer must master. The fundamental rule is this: any valid physical equation must be dimensionally consistent. Both sides of the equation must have exactly the same dimensional formula. If they do not match, the equation is wrong, guaranteed. Let us verify Joule's heating law. Power equals I squared times R. Left side, P has dimensions ml squared t to the minus 3. Right side, I squared has dimensions I squared. R has dimensions ml squared t to the minus 3I to the minus 2. Multiplying I squared by m, L squared t to the minus 3I to the minus 2, the I squared and I to the minus 2 cancel, leaving ml squared t to the minus 3. This matches the left side exactly. The equation is dimensionally consistent. Dimensional analysis has 4 practical uses. First, you can verify any equation. Second, you can derive unknown relationships by requiring dimensional balance. Third, you can catch unit errors. Mixing kilometers and meters or milliamperes and amperes will always produce a mismatch. Fourth, you can derive unit conversion factors systematically without memorization. Every unit name is a tribute to a scientist who dedicated their life to understanding nature. Let us take a moment to appreciate the human stories behind these symbols. Isaac Newton, born in 1643 in England, is arguably the greatest scientist who ever lived. He developed calculus, optics, and the laws of mechanics almost simultaneously, while isolating himself during a plague. James Joule, an English brewer by trade, conducted painstaking experiments in the 1840s, proving that heat and mechanical energy are interchangeable. His work established the law of conservation of energy. Alessandro Volta, an Italian physicist, demonstrated in 1800 that electricity could be produced chemically. His voltaic pile was the first battery and the first portable, sustained source of electric current. Georg Simon Ohm, a German school teacher, published his findings in 1827 to widespread skepticism. He was initially mocked by the scientific establishment before being vindicated and honored. Michael Faraday, who began as a bookbinder's apprentice, had no university education. Yet he discovered electromagnetic induction, invented the electric motor, and is widely regarded as the greatest experimentalist in history. And Nikola Tesla, who emigrated from Serbia to America with just 4 cents in his pocket, gave us alternating current, the induction motor, and the entire framework of modern power delivery. When you write these units, you carry their legacy forward. Let us now summarize the 5 key ideas from today's lecture. Takeaway 1. M, L, and T are the building blocks. Every mechanical quantity is a combination of mass, length, and time raised to integer powers. Takeaway 2. I is the 4th base dimension for electrical engineering. Electric current cannot be derived from M, L, and T. It is fundamentally independent. Takeaway 3. Named units equal derived dimensions. Newton, Joule, Volt, Ohm, Farad, Henry, Weber, Tesla. All of these are simply convenient shorthand for specific MLTI combinations. Takeaway 4. Dimensional consistency is a law. Any physically valid equation must balance dimensionally. Use this to verify equations, derive new relationships, and catch errors. Takeaway 5. The pattern from mechanics to electricity. Each electrical unit adds powers of I to the mechanical base. Voltage needs I to the minus 1. Resistance needs I to the minus 2. We will use these dimensional foundations to derive the fundamental circuit laws of Kirchhoff, and you will see exactly why these laws must hold, not merely as empirical rules but as mathematical necessities. Thank you for your attention, and see you in the next class.